Hello everyone, I'm Paul and today we're solving problem 3381, maximum Subarray sum with length divisible by k. This is medium and here we show you my intuition, approach and efficient solution. We are given an integer array nums and an integer k. So let's say that this is nums, k is 2, and we need to return the maximum sum of a subarray such that the size of the subarray is divisible by k. In case you don't know what a subarray is, it's a contiguous selection of elements. So for example, this is a valid subarray, this is a valid subarray, but we can't form a subarray with 2 and 4 because these elements are not contiguous. The first question here is which subarrays in this array have a length that's divisible by 2? Well, we can take 2. If we do 2 module 2, this is 0, and this means that 2 is divisible by 2. So we can take every subarray of size 2. We can take this has a sum of 6. We can take this with a sum of 3. This has a sum of 5. This has a sum of 7. Now, can we take subarrays of size 3? The answer is no, because 3 module 2 is 1. Given that this is different from 0, 3 is not divisible by 2. Now, can we take subarrays of size 4? Well, we can, because 4 module 2 is 0, meaning this is divisible by 2. Which are the subarrays of size 4 here? Well, we can take this, and the sum here is 8, 10, 11, or we can take this. The sum here is 7, 10. So these are all the valid results in this case. If the length here is 5 and k is 2, we can't take subarrays of length 1, we can take subarrays of length 2, we can't take 3, we can take 4, and we can't take 5. So we only take subarrays of length 2 and subarrays of length 4. And among all of these results, the maximum value is 11. So we return 11. Now let's start small here. Let's say that we are standing at index 0. We are here. The first question is, what's the minimum length of valid subarray if we want to consider this element? Well, we know that k is 2, so the minimum length is 2. We need to take this subarray as a minimum. So we can say that the result is initially minus infinity, and every time we keep the maximum value between the sum of this subarray and the result in this variable. So the maximum between minus infinity and 6 is 6. And now we can keep adding chunks of size k to this subarray. Why? Well, because if we add 2 to k, this will still be divisible by k. So we can add these two elements, and here the total sum is 11. So we replace this with the maximum between 6 and 11, meaning 11. And this is it. We cannot take more chunks of size 2 because we only have one element left. Now, what if we start from this index? What's the minimum size of a valid subarray starting from here? Well, we can take these two elements. Here the sum is 3. And the maximum between 3 and 11 is 11. So we keep 11 and continue. Now we're checking if we can add another chunk of 2 here. We can add these two elements. So we can grab all of this. And here the sum is 7 plus 3, meaning 10. And given that 10 is smaller than 11, we keep 11 here. And that's it. We can start from here and take the first k elements because we have already done this. Remember, first when we were here, we took these two elements and then we took these two. So we have already done this part. So as you can see, we can have two possible starting positions, meaning we can have k starting positions. The amount of starting positions is given by k. If we start here, we take this, then this, and if we start here, we take this, and then this, and so on. If k was free, this would continue. Now let's say that we are given this input. Here we have two starting points because k is 2. Remember that the amount of starting points is given by k. So first we are at index 0, and Now we are taking the first chunk of size k, meaning 2. The sum in this subarray is 2, so the result is the maximum between minus infinity and 2, meaning 2. And the current sum for the iterations from index 0, the current sum right now is 2. Now we can add another chunk of size 2, meaning we add this, and if we follow the previous logic, here we would add minus 10 to the current sum, so this is now minus 8. And given that 2 is greater than minus 8, we keep 2 in the result, and now we are here, the sum here is 4, so the current sum is 4 plus minus 8, meaning minus 4. And here we have a problem because the result for this input is this subarray, meaning 4, but here we get 2. The problem is that we are considering this subarray, this one, and this one only. We are never considering this subarray. So it looks like we are missing something here. And the trick here is the following. Let's step back for a moment. We are here, the result is 2. We are about to take the next chunk of 2, and here the current sum is minus 8. So, given that this is smaller than 0, maybe it's best to forget about all of this and start a brand new subarray from this point, because we are trying to get the maximum sum of any subarray. So if we start a brand new subarray from this point, we can say that the current sum is 0 again. And now we are starting all over again. We take the sum of the current subarray, 2 plus 2 is 4, and the current sum plus 4 is 4. The maximum between 4 and the result is 4. And now this is the correct result. So if the current sum is smaller than 0, now it's 0, and we start all over again with a new subarray. Now we need to do exactly the same starting from index 1, because k is 2, so this is the last starting point. We take the first chunk of 2, and 1 plus minus 5 is minus 4, so the current sum is minus 4. And the maximum between minus 4 and 4 is 4, so we keep 4 here and continue. Now we can take this chunk, and given that this is smaller than 0, now this is 0. And we take the sum of this, minus 5 plus 2 is minus 3, and the maximum between 4 and minus 3 is 4, so we continue, and we can't take this. We have no more chunks of 2 to take, so that's it. Now we have already tried every chunk of 2, starting from the first k indices, so we return 4. Now we have one last problem here. How can we get the sum of any subarray in big O of 1 time complexity? Because we can have up to 2 times 10 to the power of 5 numbers, and this is a lot. So let's say that we have this array. We are building an array of the same size, and we are calling this P for prefix sum. In this array prefix sum, we are storing the sum of every element here up to the corresponding index. So first we are here, the sum up to this point is 1. Next we are here, and the sum is the current number plus the accumulated sum. 1 plus 1 is 2. Next we are here, and 2 plus 2 is 4. Next here, 2 plus 4 is 6. Up here we have the indices. So now let's say that we are trying to get the sum of this subarray using this prefix sum array efficiently in big O of 1 time complexity. So we are trying to get the sum of this subarray. Well, we can take the right bound and subtract the corresponding value in the prefix sum for the left bound minus 1. We do 6 minus 2, and this is 4, meaning this is the sum of the elements in this subarray. And just to be clear, we are trying to get the sum of the elements in this subarray, so we can take the prefix sum for the right bound, meaning the sum of all of this, and subtract the sum of left bound minus 1, meaning the sum of all of this. That's how we get this chunk, meaning this chunk, which is exactly what we want. And finally, in case you are wondering what's this algorithm, it's called Kedane's algorithm. You can Google this if you want. We use it to get the maximum sum of subarrays, and here we are using it to get the maximum sum of subarrays that are made with chunks of size k. So it's basically the same idea. Now, with all of this in mind, let's go with the code. First, we say n is the length of nums. Now we can build our prefix sum array. We will call this p. This is an array with nums 0 times n initially. And now we need to fill this. So for I in range from 1 to n, pi is pi minus 1 plus the current number. The result is initially minus infinity. And now we can iterate every starting point. So for I in range k, current is I every time. We are using this because we need to implement a nested for loop here. We are using a while loop. The current sum is initially 0, and while current plus k is smaller or equal to n, the sum of the current subarray is the following. For this, we can use the prefix sum. The right bound is at current plus k minus 1, and the left bound, which we need to subtract, is at current minus 1. Now, it might be a case that current minus 1 is out of bounds. If this is smaller than 0, for this side of the argument, we should use 0 instead. So we use this if current minus 1 is greater or equal to 0, else we use 0. And here we use parentheses. And now we need to add this sum to the current sum. So cs plus equal s. And the result is the maximum between the result and cs. And every time we need to take another chunk of k numbers if possible, if current plus k is smaller or equal to n. So we can say current plus equal k. Now remember that the current sum could be negative, and if so, we want to start a new subarray. And we do this by resetting cs back to 0. So if this is smaller than 0, now cs is 0. We check this every time. Now, finally, we can return result. So this is the entire code. Now let's submit this. As you can see, this works and it's very efficient. Here, time complexity for this part is big O of n, and time for all of this is big O of n. And you can think about this like this. If k is 1, this means that the outer loop runs only once and the inner loop runs n times. And if k is n, this outer loop will run n times and this inner loop will run only once every time. So this is overall big O of n. And overall time complexity here is big O of n. Space complexity is also big O of n because we need to build this prefix sum array. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.